Hey friends, Dr. Borole is here. Today our focus is on the another modulation technique called frequency modulation. In frequency modulation, the instantaneous frequency of the carrier signal is made proportional to the instantaneous value of the modulating signal. The amplitude of the carrier signal remains constant in FM, whereas the variation in the frequency contains the information. Let us define the carrier signal and the modulating signal. Let the modulating signal is represented as xt or say em, that is equal to em capital cos of omega m into t. The omega m can be twice by fm. Let the carrier signal be denoted as ct. Here t in the bracket indicates the function of time, or it can be also denoted by the instantaneous value ec. Suffix c indicates the carrier signal, that is equal to capital EC sine of omega ct plus phi, whereas capital EC is the peak amplitude of the carrier signal. Let us also define the modulated signal EFM as capital EFM sine of theta FM, whereas theta can be defined as omega FM t plus phi. In the modulation, as we have defined, the frequency of the carrier is made varied in proportion to instantaneous value of the modulating signal. Let us see the waveform of frequency modulated signal with respect to modulating signal. Let us use here the modulating signal as a low frequency sinusoidal signal and the carrier signal as high frequency sinusoidal signal. If you see, when the modulating signal is 0, there is no change in frequency of the modulated signal. Means the modulated signal have frequency same as the carrier signal free running frequency omega c. When the instantaneous value of the modulating signal is increasing, the frequency of the modulated signal is increased. When the amplitude of the modulating signal is decreasing, the frequency of the modulated signal is decreased. This is done by a circuit called frequency modulator. So therefore, you will see that when the modulating signal amplitude is maximum, the frequency of the modulated signal will be maximum. When the amplitude of the modulated signal is minimum, the frequency of the modulated signal will be minimum. So same thing is mentioned here. The frequency of the modulated signal is now proportional to the instantaneous value of the modulating signal. We have seen that the rate of change of frequency, that is d omega fm by dt, is proportional to the frequency of modulating signal. It means that if the modulating signal is changing faster, the frequency of the modulated signal is also changing with the faster rate. We also note from the waveform that the frequency modulated signal amplitude remains constant. The information is contained in variation in the frequency. Let us now estimate the mathematical expression for frequency modulated wave. Let us repeat here the expression for the carrier signal. EC is equal to EC sine of omega CT plus phi. That is nothing but EC sine theta. Here in the diagram, you will see a phasor notation. A phasor with amplitude A when rotated in the complex plane with the frequency omega. Theta is nothing but the angle shown here. Rate of change of theta, that is d theta by dt, is nothing but the angular frequency omega. So therefore, omega is nothing but d theta by dt. Simplifying this expression, taking d theta on left side and remaining terms on right side, and estimating the value of theta by taking the integral of right hand side, that is nothing but theta equal to integral of omega dt. This is general expression. Now let us apply this to our frequency modulated signal derivation. In frequency modulation, the frequency of the carrier is made proportional to instantaneous value of the modulating signal, that we know. So therefore, we can express same thing by the mathematical expression. Therefore, omega Fm is say omega C plus Kf into Em, where omega C is the frequency of a carrier signal when modulating signal is 0, where Kf is the proportionality constant. So what this expression tells us? This expression tells us that the frequency after modulation, that is omega Fm, is a function of a modulating signal. So it is varied from omega C to higher value when Em is positive, and it will reduce from omega C to lower value when omega M is negative. Kf is just a proportionality constant. For the sake of simplicity, we can assume Kf as 1. That is possible. We will replace the instantaneous value of the modulating signal Em by its expression Em cos of omega mt. Therefore, from the expression of theta above, theta Fm is nothing but integral of omega dt. Now put the value of omega as omega Fm. So integral of omega Fm into dt is theta Fm. Substitute the value from the above expression in the integral and solve the integral. So therefore, theta Fm comes out to be omega c into t plus kf into Em sine of omega m t plus phi 1 divided by omega m. Since phi 1 is a constant phase angle, for the sake of simplicity, we will ignore it further, or we will consider it 0 for the sake of simplicity. So therefore, now we get the value of theta Fm, and we will substitute this in the carrier signal wave equation to get the modulated signal. And therefore, modulated signal is given by EFM as a function of t, that is EC sine of theta Fm. Now replace theta Fm by the expression we have just obtained. That is EFM is equal to EC sine of omega CT plus KF into EM by omega M sine of omega M into T. Here our expression is in the form of angular frequency omega m. Very well, you can express the frequency in hertz also. That is, frequency can be denoted by f, that is, say, modulated signal frequency can be denoted by f of fm. And we know the relation between f and omega. Omega is equal to 2 pi f, and therefore f is equal to omega by 2 pi. And therefore we get here ffm is equal to omega fm by 2 pi. Substitute the value of omega fm here, that is omega c by 2 pi plus kf into em cos of omega mt by 2 pi. Now we will have omega c by 2 pi as fc, and therefore f of fm is equal to fc plus kf into em by 2 pi cos of omega mt. That is in terms of frequency in hertz. You can very well use the expression in terms of angular frequency also, that is this omega c is equal to this one. Omega c is equal to, or omega fm is equal to omega c plus kf into em sine of omega mt plus phi 1. From the above expression we have just derived for the frequency, we can estimate the minimum and maximum frequency content in the FM wave. The maximum frequency is given by FFM max. When FFM is max, when cos of omega m into t is 1. So therefore, we are getting FFM max is equal to FC plus KF into EM by 2 pi. Whereas the minimum value of the frequency is obtained when cos of omega t in the above expression is minus 1. So therefore, f of fm minimum is equal to fc minus kf into em by 2 pi. From these two expression, we found that the frequency is varied from minimum to maximum when the modulating signal is changing from minimum amplitude to the maximum amplitude. Let us estimate the frequency deviation from these two expressions. Frequency deviation Fd is defined as the change in frequency from the carrier frequency. So it can be FFM max minus FC, or it can be FC minus FFM minimum. So whenever you subtract or add FC in this expression of FFM max or FFM minimum, you will get the factor Kf into Em by 2 pi as a frequency deviation. As we know that the carrier frequency is now changed from maximum value to minimum value, and therefore the total carrier frequency swing is twice of frequency deviation Fd. Let us estimate a parameter that is called modulation index. It is denoted by a factor mf, or also denoted by delta or delta f. The modulation index mf is defined as the ratio of frequency deviation fd to the modulation frequency fm. It is also indicated by the Greek letter delta. Same thing is written here. Therefore, MF is equal to frequency deviation divided by modulating frequency. That is FD by FM. And therefore, substituting the value in this expression, MF is equal to K into EM by 2 pi, that is FD, divided by FM. Whereas 2 pi FM is omega, and therefore 2 pi FM is omega M. And therefore, the modulation index MF of the frequency modulated signal is approximately coming out to be Em by omega m, considering Kf as 1. If you see the unit of this modulation index, you will see it is unitless. And the range of Fm is from 0 to infinity. You will see the expression. There is no bound on the value of Em as well as omega m. Em can be any value and omega m can also be any value. And therefore, the ratio of Em by omega m may be varied from 0 to infinity depending on the values of Em and omega m. Therefore, the modulated FM signal is given by EFM is EFM sine of omega FM t, that is equal to EC sine of omega CT plus KF into EM by omega M sine of omega M into T. We will replace here Kf into Em by omega M by Mf, and therefore EFM, that is the modulated signal now, equal to EC sine of omega CT plus MF sine of omega M into T. And we here observe that by changing the modulation index, you will see there is a change of bracketed term. That is nothing but the frequency of overall modulating signal. And the rate of change of frequency of the modulating signal is also the function of omega m, that is the frequency of modulating signal. Alternatively, you can use the cosine wave also. Here, we use the sinusoidal term for expressing the carrier signal, whereas you can very well use the cosine signal also to derive the expression for modulated signal, because sine and cosine signal, there is only difference of phase shift of 90 degree. Therefore, we can summarize that the modulated signal EFM is EC sine of omega CT plus MF sine of omega M into T, whereas EC capital is the peak amplitude of the FM wave and which remains constant, whereas the bracketed term is the frequency of the modulated signal, and you will see that it is a function of modulating signal, and modulating signal is incorporated in the modulation index MF we have just defined, because MF we have defined as Em by omega M. In FM broadcasting, the maximum value of the deviation FD is 75 kilohertz used in practice, and the maximum modulating frequency for the FM is used up to 15 kilohertz. Therefore, modulation index MF for the practical FM broadcasting station is FD by FM, that is 75 kilohertz by 15 kilohertz, that is 5. Now let us estimate the power in FM signal. We know power is nothing but V square by R. So we know the amplitude of the modulated signal, that is EC by root 2, that is the RMS value of the modulated signal voltage, square of it, EC by root 2 square into 1 by R, that is nothing but V square by R. Simplify it, you are getting it. The power transmitted in the form of modulated signal as EC square by 2R. When R is 1, this becomes equal to EC square by 2. The various questions those are asked on frequency modulation in the university exam paper are listed here. So whatever we have discussed up till now, same is asked in the university examination for 6 to 7 marks. And it is repeated most of the time. So therefore, here we have just finished the frequency modulation and frequency modulated signal expression. Now let us see the frequency spectrum of frequency modulated signal. What is frequency spectrum? Frequency spectrum is nothing but the set of frequencies those are present in the modulated signal, and it is expressed as XY graph. On x-axis there is a frequency, and on y-axis there is amplitude corresponding to the particular frequency component. So we repeat here the expression of frequency modulated signal, that is EFMT is equal to EC cos of omega CT plus MF sin of omega MT. As we know, the cosine component cos of this bracketed term is nothing but the real part of the expansion of e raised to I theta. We know e raised to I theta is equal to cos of theta plus I sin theta. And therefore, cos theta is basically a real part of e raised to I theta. We apply that identity here. So here cos of omega ct plus mf sin of omega mt is a real part of e raised to j omega ct plus mf sin of omega mt, where the bracketed term is theta. And therefore real part of e raised to j theta is nothing but this cosine term. We can further simplify omega ct plus mf sin of omega mt is divided in two parts, that is e raised to j omega ct into e raised to j mf sin of omega m into t. The Bessel expansion of e raised to j theta, here theta is mf sin of omega mt, is given as sigma of n equal to minus infinity to plus infinity jn mf e raised to jn omega mt, whereas jn mf is the Bessel coefficient. We will apply the definition of Bessel expansion to our frequency modulated signal expression. So therefore, we are getting the frequency modulated signal EC into real part of e raised to j omega ct into sigma of n is equal to minus infinity to plus infinity jn in bracket mf e raised to n omega mt. See here, e raised to j mf sin of omega mt expansion is just substituted in the expression. Now here we will take e raised to j omega ct inside the summation bracket. And therefore, this e raised to j omega ct is taken here as e raised to j omega ct into e raised to j n omega ct, that is multiplied by the Bessel coefficient j n mf. Now simplify this. E raised to a into e raised to b, that is equal to e raised to a plus b. So therefore, we get EFMT is equal to EC, real part of sigma of n is minus infinity to plus infinity, the Bessel coefficient j and mf, e raised to j omega c plus n omega m into t. Whereas again we will use the exponential term expansion e raised to j theta is equal to cos theta plus j sin theta. Whereas cos theta is nothing but the real part. So here real part of e raised to j omega ct plus n omega t is nothing but cos of omega c plus n omega m into t. And therefore we will get the final expression of a modulated signal EFM is equal to EC under the summation sign n start from minus infinity to plus infinity j n mf cos of omega c plus n omega m into t. This signal can indicate and expanded further. This summation bracket can be rewritten in the form of sum of the individual terms. Consider n is equal to 0. When n is equal to 0, you are getting the first term. EC J0 MF cos of omega CT, because MF n is equal to 0 here. So n omega t is 0. When n is 1, then it becomes J1 MF cos of omega c plus omega m into t. When n is minus 1, then you are getting J1 MF cos of omega c minus omega m into t. For j is equal to 2, you are getting the second term and so on. So you are getting for n plus positive the summation term, and when n is negative, you are getting the subtraction term. And this series will be continued from minus infinity to plus infinity. So what we observe from this expression is the first part EC into J0 MF cos of omega CT. This is just the carrier frequency signal EC cos of omega CT with a multiplier J0. So same frequency of carrier. So you are getting a carrier wave in the frequency modulated signal as one component. And you are getting sum and difference frequency component of carrier signal and modulating signal from minus infinity to plus infinity. So the frequency modulated signal ultimately consists of infinite number of frequency. One frequency is omega c plus omega m. Second frequency is omega c minus omega m. Third frequency is omega c plus twice omega m. Fourth frequency is omega c plus thrice omega m. Fifth frequency is omega c plus 4 omega m and so on. Whereas the difference frequency component is varying from omega c minus twice omega m, omega c minus thrice omega m, omega c minus 4 omega m and so on. So ultimately there are so many sinusoidal signals. So ultimately the frequency modulated signal consists of one carrier component and infinite number of sidebands. And the sideband frequency can be omega c plus n omega m or omega c minus n omega m. The same thing is shown here. Only two coefficients J0, J1 and J2 are shown. So first part is omega c. J1, second term is a pair of sideband shown here. Omega c plus omega m is one sideband and omega c minus omega m is another sideband. So ultimately, cos of omega c plus minus omega m into t is a pair of sideband. So there are generation of multiple pair of sidebands. Now this mathematical expression can be graphically plotted as a XY graph, and that is nothing but the spectrum of a FM signal. Whereas the coefficient J0 to Jn at various values of modulation index MF is shown in a table of Bessel functions here. You will see here highlighted when modulation index is 1, the value of J is changing from J0 to J3. Other coefficients are 0. Whereas when modulation index is 10, then you are getting the J coefficient, those are significant up to J14. So higher the value of modulation index, more and more J coefficients are significant. And therefore, in the frequency spectrum, we will consider the significant magnitude pair of subbands. What are the observations from the same expression? FM wave consists of a carrier signal. That is first observation. Second, FM wave ideally consists of infinite number of subband pairs. You will see here omega c plus omega plus minus omega m, omega c plus minus twice omega m and continued up to n omega t up to infinity. So it gives infinite number of sidebands. Amplitude of the carrier signal remains constant and the amplitude of the modulated subband is depend on the coefficient of a Bessel function called J function. The spectrum of FM signal is generally wider than AM signal because in AM signal we will see only a pair of sideband is generated, whereas here multiple pairs of sideband are generated and therefore the spectrum of generated frequency modulated signal is wider. The number of significant sideband also depends on the value of MF. You will see from this table when MF is higher, the significant number of sidebands are going up to 14 for MF is equal to 10. If MF is equal to 15, it can be continued further up to J20. So 20 number of sidebands are significant. As instantaneous value of the modulating signal increase or decrease, the frequency deviation and modulation index is also increasing or decreasing. That gives rise to increase in number of side bands because we have seen the expression of FD and MF. FD and MF are the function of the modulating signal amplitude EM, and therefore with the variation of EM there is variation in FD and MF as well as in number of sideband. The expression we have seen for a frequency modulated signal can be plotted as a graph. So we will observe from this graph there is a carrier frequency signal which is of a frequency fc. Let us see the expression again. See here, the first part, the frequency is omega c, that is 2 pi fc. So first part or carrier is varying with the rate 2 pi fc, that is with the frequency fc. and having amplitude J0 into MF into EC. Therefore, the first component is having frequency FC with the amplitude J0 MF into EC. Now let us see the second pair. Second pair have the frequency omega C plus omega M and omega C minus omega M. That is FC plus minus FM. So you will see here FC plus FM having amplitude J1 into MF into EC. And counterpart of the pair is J1 into MF into EC as amplitude and frequency is FC minus FM. Similarly, for second pair of sideband, the frequency is Fc plus twice Fm and Fc minus twice Fm. Whereas for third component, the frequency is Fc plus thrice Fm and Fc minus thrice Fm, and so on. And we will consider only up to the significant sideband amplitudes. When the sideband amplitude is very, very small, we can ignore it. So, we will see here there are so many frequency components generated. In AM, we get only three components: the carrier component, the lower sideband component Fc minus Fm, and the upper sideband component Fc plus Fm. Whereas here multiple upper sideband component at integral multiple of Fm are generated, and lower sideband at the integral multiple of Fc minus Fm are generated. So therefore, frequency modulation gives rise to multiple frequency component, and this graph is called as frequency spectrum of a frequency modulated signal. Let us see what is the effect of modulation index on frequency spectrum. When modulation index is 1, you will get Fc plus Fm and Fc minus Fm component, because here we can estimate the amplitude coefficient J0 MF, and that is given from the expansion table. See, when MF is 1, J0 is 0.77, J1 is 0.44, J2 is 0.11 and J3 is 0.02. Putting that in this expression, you are getting the amplitude of these bars, frequency bars, called as sidebands, upper and lower sidebands. Another thing we will observe here, that when modulation index is 1, there are three upper sideband and three lower sideband. Means three pair of sidebands with the carrier is generated. Because if you see the Bessel coefficient table, see there are four components: J0, J1, J2 and J3. Means there are only four components. J4, J5, J6, J7 are having insignificant amplitude and therefore ignored. Whereas when the modulation index is 2, you will see there are four upper sideband and four lower sideband. Means there are four pair of sidebands. See here in the table again, when MF is 2, there are 1, 2, 3, 4 and 5. Means carrier is 1 and 4 sidebands. And other sidebands, upper sidebands are having not significant amplitude, therefore ignored. So, what we observe from this Bessel coefficient table, when modulation index is increasing, the number of sideband present in the spectrums are increasing exponentially. There are some questions on the frequency spectrum and frequency modulation. Those are shown here. They are expecting that you have to write the expression and explain the expression meaning. But whenever you know the details of the derivation of the expression, then very well you can able to explain what is the meaning of the spectrum. So we can conclude that the ideal bandwidth of frequency modulated signal is FF max minus FFM minimum. Whereas ideal bandwidth is infinity, because we have seen there are infinite number of frequency sidebands are generated. Practically, the bandwidth can be twice of FM into number of significant sidebands. The bandwidth of the FM signal is found to be much higher than AM, that is amplitude modulation, and therefore multiple FM stations can consume large bandwidth compared to AM stations. The approximate practical bandwidth by Carlson rule is given by bandwidth is equal to twice delta plus f of Fm max. The Carlson rule gives the correct result for modulation index greater than 6. For lower values of modulation index, the error will be introduced. And that's all, friend, about the frequency modulation. Some of the examples are shown here. Let us see the first example. The radio signal frequency modulated signal. The center frequency is given as 160 megahertz. That is the carrier frequency. If the modulating frequency is 5 kilohertz and the frequency deviation is 20 kilohertz, they ask you to calculate the carrier swing and the modulation index. We already have the expression derived for both of the parameter. So let us see what is given. The carrier frequency is given 160 megahertz. The modulating frequency is given 5 kilohertz. And the deviation, frequency deviation, f max minus f minimum, that is fd, is given 20 kilohertz. Carrier swing is given by twice of fd or twice of delta. So twice of 20 kilohertz is the carrier swing. The modulation index is given by FD by FM. That is nothing but delta by FM. So 20 by 5, so modulation index is 5. That is so simple. The example 2 is just a repetition with the different values. And they are asking you the frequency deviation, carrier swing, modulation index, and lower frequency attended by the FM wave. Here what is given? FC is given 110 megahertz. F max is given, that is modulated signal maximum frequency is given 110.10 megahertz and frequency of modulating signal is 10 kilohertz. Find delta F, carrier swing, modulation index and minimum frequency F minimum. So delta F is given F max minus FC. F max is given 110.1 megahertz minus 110 megahertz. So that is the total variation in the frequency, that is deviation. And that is zero point 0.1 megahertz, that is 100 kilohertz. Carrier swing is nothing but twice delta or twice delta F. So delta F here is 100 kilohertz. So maximum variation carrier swing is twice of 100 kilohertz, that is 200 kilohertz. Modulation index MF is delta F by Fm. So 100 kilohertz by 10. So modulation index is 10. The lowest frequency can be obtained as F minimum is Fc minus delta F. And maximum frequency we have seen F max is equal to Fc plus delta F. So here F minimum is Fc minus delta F. Minus delta F is already calculated, that is 100 kilohertz. So 110 megahertz minus 0.1 megahertz, that is 109.9 megahertz. So this signal is varying from 109.9 megahertz to 110.1 megahertz. When the modulating signal is changing its amplitude from maximum to minimum. And that's all, friends. There are various additional examples shown here. They are alternatively asking the same thing again and again. So you can solve these examples for practice. Let us understand the effect of noise on AM and in FM. See, when the modulated signal is propagated through a media, unwanted noise is getting added in the signal. Unwanted signal is added as amplitude variation always. And therefore, in amplitude modulation case, this noise gets interfere with the information because in AM, the noise is variation in amplitude and signal is carried in the modulated signal also in the form of amplitude variation. So they badly mixed up and therefore AM is susceptible to noise. Whereas in frequency modulation, even though the carrier frequency after modulation gets altered by noise in the form of change in amplitudes, then no problem. At the receiving end, we can clip off the amplitude variation safely because we know that in FM, there is no information content in variation in amplitude. And therefore, even though noise gets added in more frequency modulated signal, it can easily remove at the receiving end just by slicing the amplitude at a particular level and noise can be clipped off. Here, the following table shows the comparison of AM and FM, in which basic definitions are shown first for the comparison. In AM, the modulating signal varies the amplitude of the carrier, whereas in FM, the frequency of the carrier signal is made proportion to the modulating signal. The graph of amplitude modulated signal is shown here and the graph of frequency modulated signal is shown under FM. That is one comparison point. The modulation index equations are shown as a comparison point. Whereas amplitude modulated signal is continuously varied, whereas amplitude of a frequency modulated signal remains constant. Bandwidth of amplitude modulated signal is twice FM, whereas bandwidth of the frequency modulated signal is twice delta plus FM, where delta is the frequency deviation. Noise immunity in AM is poor, whereas noise immunity in FM is very good. Number of sideband present in AM are only two, means one pair of sidebands are generated. So spectrum contains only one pair of sidebands. Whereas in FM we have seen spectrum consists of n number of significant sideband depending on the value of modulation index MF. The information contained in AM in amplitude variation, whereas in FM the information contained are in frequency variation. Complexity of AM is less compared to FM. AM is mostly used for radio and TV broadcasting. In radio receivers, normally the audio signal is used for transmission and that is mostly using the amplitude modulation. In television also, for broadcasting purpose of audio and video signal, AM is used. Whereas FM is used also for radio stations, those are called frequency modulated radio station or FM stations. It can be used for police wireless and security services also. But range of reception of FM is much less than the range of reception of amplitude modulated signal. And therefore, for larger area reception, AM stations are better, whereas FM stations are of very good quality, but their reception is over the smaller range of around 10 square kilometer. Whereas AM station can be available up to 50 to 100 square kilometer area. And let us see how FM can be generated. FM can be generated by FM transmitter. The block diagram of a FM transmitter is shown here. Basically, it consists of a frequency modulator called phase modulator. And it will take one signal as a modulating signal, that is the signal which you want to transmit, maybe audio signal or baseband signal. RC filter is used to eliminate the unwanted noise and limit the bandwidth of the modulating signal. Whereas carrier is required to increase the frequency of the modulated signal, and therefore here two signals are mixed in the modulator and it will generate the frequency modulated signal. This is the particular diagram of simple Armstrong frequency modulation system. Whereas the second diagram shows the super heterodyne FM transmitter or FM generation system. The modulating signal is there. Audio equalizer is optional. It is basically a filter which can modify the various frequency bands of the modulating signals. Again, it consists of a phase modulator which will mix the frequency of crystal oscillator with the modulating signal. So FM will be generated at the output of the phase modulator 1. The mixer circuit takes the output from the frequency modulated signal and it will be multiplied by the mixer with the another crystal oscillator frequency. And this frequency multiplication is used for boosting the frequency of the modulated signal. The multiple frequency mixers are used to increase the frequency of the modulated signal to the required band. Now, finally, we are getting the output frequency modulated here at the output of say mixer 2. But this signal is having low in power and amplitude and therefore this signal will be amplified in amplitude as well as in power level by using power amplifier. Most of the time these power amplifiers are class C amplifiers with the tuned circuit at the output, and then high power FM signal generated by the amplifier is then connected to the transmitting antenna. So that was in short the FM transmission system. Now when this FM signal is radiated, it will be received by various receivers. So let us see now how the receiving system is called FM receiver. So here the antenna will catch the signal which is transmitted by the transmitter. The signal from the antenna is very weak. So therefore it first needs to be amplified. So amplitude of the signal will be increased by using RF amplifier. The RF amplifier additionally provides a selectivity function. There is a local oscillator circuit and a mixer circuit in the super heterodyne receiver, similar to the AM receiver. So when the FM signal is received here, it will be mixed with the local oscillator frequency. So the generated signal will be now shifted around a different carrier called as intermediate frequency. So you are getting the frequency modulated signal with the center frequency is intermediate frequency. And therefore, this intermediate frequency is further amplified with the amplifier called IF amplifier. The IF amplifier output is given to a limiter circuit because we know if there is an amplitude variation in FM, that is because of noise. So amplitude variation can be eliminated by clipping of the amplitude of the IF amplifier signal. So any noise generated amplitude change can be eliminated. So finally we are getting at the output of the limiter a FM signal shifted around the carrier frequency that is equal to intermediate frequency IF. The most of the practical FM radio receiver use the intermediate frequency of 10.7 megahertz, irrespective of the stations received. For different FM station, we will tune the receiver by changing the local oscillator frequency to the carrier frequency of that FM station. Whereas mixer output will be always centered around the intermediate frequency. Therefore, all the amplifier blocks further and the discriminator and other blocks are worked at the constant frequency of intermediate frequency only. Whereas RF amplifier and mixer and local oscillator circuit gives us the capability to tune our radio receiver at different frequency modulation stations and generates constant modulated signal at intermediate frequency of 10.7 megahertz. Discriminator is also called as demodulator, called frequency demodulator circuit. This frequency demodulator have a function which will convert the change in frequency to change in corresponding change in amplitude. So therefore, at modulation, we change the frequency proportional to the amplitude of modulating signal, and at demodulator, we will change the change in frequency to the original change in amplitude of the modulating signal. So whatever the output of discriminator is similar or close to the modulating signal. The de-emphasis is applied to the modulating signal available from the discriminator, and then it is connected to a modulating signal amplifier. In case of audio signal, it is a audio amplifier, and then it is reproduced on the loudspeaker. So when the transmitter hears, for example, you have a modulating signal as audio, then this audio signal is used to frequency modulate the carrier signal that is generated by the crystal oscillator. The frequency can be enhanced and boosted by another crystal oscillator, and it is transmitted by the transmitter. After transmission, it is received by the receiver. You can select the receiving station by selecting the local oscillator frequency corresponding to that station. And then further, the demodulator will extract the frequency from the frequency modulated signal, the original modulating signal, that is the audio signal, and you will listen it on the loudspeaker. Whereas transmitter and receiver can be few meters away from each other or few kilometers away from each other. The channel can be a wired channel or wireless channel, and most of the time the channel is a wireless channel, and the area of coverage is in the range of tens of kilometers for FM station. And that's all about the frequency modulation technique, its expression of frequency modulated signal, then spectrum of frequency modulated signal, and frequency modulation transmitter and frequency modulation receivers. The following table shows the comparison of AM and FM receivers. Whatever we have discussed, same points are listed in the tabular form. I will just repeat it. The operating principle of AM receiver is super heterodynamic and FM receiver is super heterodynamic FM receiver. The value of IF in AM receiver is 455 kilohertz, whereas in FM receiver it is 10.7 kilohertz. The range of input frequencies for AM receiver is from 530 kilohertz to 1650 kilohertz, whereas for FM receivers it is 88 megahertz to 108 megahertz. Amplitude limiters are not required in AM receiver because the information is contained in amplitude variation itself. Whereas in FM receiver, limiters are used to eliminate the noise. Quality of reception is somewhat poor because it is affected by noise, which gives rise to amplitude variation and badly mixed up with the signal in AM receivers. Whereas in FM receivers, quality of reception is good because by limiting the amplitude, we can eliminate the noise at FM receiver stages. Whereas here, the block diagram and various waveform at various stages of FM receiver are shown. Here, the signal received at the antenna, that is the FM radio station signal, that is frequency modulated signal. Oscillator signal is a constant frequency signal which is same as the carrier of the selected radio station. And therefore, you will see here constant amplitude, constant frequency signal. These two signals are mixed by mixer, and output of the mixer is again a frequency modulated signal. Only difference is that here the carrier frequency is changed from the station carrier frequency to intermediate frequency. Even though station is changed, local frequency oscillator frequency is also changed proportionately, and therefore IF remains constant. So therefore next block after this mixer operates at the constant bandwidth. The IF amplifier, just the amplitude of the frequency modulated waveform is increased. If there are any variation in the amplitude, those can be eliminated by the limiter, and therefore you will get here the noise eliminated frequency modulated signal at the output of the limiter with carrier frequency is equal to intermediate frequency, say IF. This signal is then given to the FM detector called as FM demodulator or discriminator. It will convert the change in frequency information to corresponding amplitude change. That is nothing but your modulating signal. This modulating signal will be amplified by the modulating signal amplifier and power amplifier. In case of audio signal, the modulating signal is a audio signal and therefore amplified by audio power amplifier and then connected to the loudspeaker. Various advantages of FM are listed here. Whatever we have listed in the comparison table, same thing is listed here. FM have advantages over AM because FM is having good noise immunity. FM requires low power for transmission. Area of coverage of FM is large with the same amount of power transmitted compared to AM. Transmitted power remains constant in FM. Why it is so? Because amplitude of the modulated signal remains constant. Whereas in AM, the amplitude is varying and we know the power is proportional to V square by R. And obviously if amplitude varies, the power transmitted also varies. All the power transmitted by FM station and frequency modulated signal is useful power. Whereas in AM, the information content in sidebands. Whereas carrier signal present in the AM modulated signal is an unwanted signal, which is just a wastage of power because it doesn't contain any information. And therefore, compared to AM, in FM, the transmitted power all is a useful power. What are the disadvantages of FM? Obviously, we have seen the spectrum, very large bandwidth is required compared to AM. Range of transmission is limited to line of sight due to space wave propagation in FM. Means in FM, we are using space as a channel or atmosphere as a channel. And therefore, the high frequency signal always gets attenuated by the transmission media and therefore range of transmission is limited. Transmission of FM signals, transmission as well as reception requires the complex equipment. Where FM is used, it is used for radio broadcasting like stations Vivid Bharati, Radio Mirchi, FM radio, etc. Many FM stations are available now. It can be used for sound broadcasting in television receiver. In TV receivers, the picture information transmission is done through amplitude modulation, whereas sound transmission is done through frequency modulation. FM can be used for satellite communication and police wireless system also. And it can be used for point to point communication like walkie talkie. Some of the additional examples on FM and related calculations are shown here. You can go through it, and that's all about the frequency modulation technique, friends.